Hey guys, I just wanted to do a quick review of class 15 for a couple of you guys that missed it. Let's see, it might be giving me a little bit of feedback. Let me do this. There we go. Okay, so back in class 14, we talked about the unstandardized regression equation and standardized regression equation. So here you can see a nice scatter plot of fertility and life expectancy. And we have some different countries that are plotted on here. And we can draw a regression line right through there. You can see if we come up with the actual unstandardized regression equation, this is what we get. Y hat equals negative 4.64 times x plus 82. So we're able to put any number into that and give a predicted y hat. So let's put 5 in there. We can plug in 5, and what we would get, that life expectancy for a country that had 5 a number of births per woman would be about 58.5 years. Okay, so that would be going up to the line, as you can see here, and then going across. So that's the graphical representation of exactly what we just did here by plugging in 5 and then getting our y hat to be 58.5. Okay, so let's say we turn that into the standardized equation. So the standardized equation, as you all guys know, does not have a y-intercept because it's 0, because it's standardized. So if you look at the equation right here, we have just the slope, we have the z of x, and we have z hat of y. So you can see here that we have to make sure our y and x axis are also in standardized form. So you can see here zy and then z of x. So this would be plotted like this. This would be plotted like this. Same exact line, exact thing. So let's say we wanted to get 5 again, but we want to do it in z-scores. So 5 is about 1.57. We just plug that right in here to z of x, multiply that by 0.8 to get negative 1.26. So that would be z hat of y. And you can see that would be represented graphically by going up right there and going over. And these are the exact same. Both of these are the exact same line. Just the only thing that differs between them is this is standardized, so it's in forms of zy and zx, and this is unstandardized, so this is in raw. So this is really important to remember. The standardized regression equation and the unstandardized regression equation use the same regression line. They have the same prediction points, and they produce the same predicted value of y. The only difference is that one uses unstandardized values and the other uses standardized values. So you need to make sure you're familiar with terminology. So right here, if we're looking at the unstandardized regression equation, you see that this right here is the unstandardized slope. This is also known as the unstandardized regression coefficient, or B. So this right here is going to be the unstandardized intercept, or A. Okay, so this is the standardized regression equation. This is z hat of y equals negative 0.80 times z of x. And this is going to be the standardized slope. So this is going to be the standardized regression coefficient, or beta. And as we know, the standardized intercept is always 0. Why is it always 0? Well, it passes through the point of averages. So in a standardized regression equation, the point of averages is always 0, 0. We just don't show it. It's invisible, but it's there. Okay, so 2 essential facts about the standardized regression equation. It's really nice that in the standardized regression equation, our beta is r. So our slope is always r, always. So if you look right here, we can just substitute our correlation coefficient, R, right into beta. So that's what we call, in this class, the magic formula. So z hat of y equals R times z of x. Okay, so if we want to solve regression problems in which the predictor and the criterion are z-scores, we can use this magic formula. So let's say Isabel has a score of 1.5 on her midterm, and we want to estimate her score on the final. And let's say the midterm and final are correlated at 0.5. What we can do here is just plug in the information that we know. Okay, so we know R is 0.5, so let's plug it in right here. We know Isabel scored 1.5 on the midterm, so remember that's our predictor, so that's going to be our z of x. And what we want to determine is her z-score on the final, which is going to be the criterion. So let's just do a little bit of math. So 0.5 times 1.5 equals 0.75. So our predicted score for her on the final would be 0.75. Okay. So now let's look at how to solve a regression problem in which the predictor and criterion are raw scores. So let's say Carla scored a 90 on the midterm. We want to estimate her grade on the final. So here we know a little bit more about the final and about the midterm. So we see that the mean of the midterm is 75 and the SD is 10. In the final, the mean is 76 and the SD is 8. And the correlation coefficient between midterm and final is 0.5. Okay, so it's nice if you just draw kind of like this up here. So because we're going to have to go between x, we have to convert it to a z-score and then use the magic formula to get our criterion, and then take our criterion and turn it back to a raw score. Okay, so first let's put what we know, 90. Okay, this is really important. You guys need to know your formulas. So let's convert 90 to a z-score. So it's just going to take deviation divided by SD. So deviation is going to be 90 minus 75 divided by 10. So you're going to get 1.5. Okay, so now we use our magic formula. So we're just going to do 0.5 times 0.75, or 0.5 times 1.5 to get 0.75. And then we're just convert that back. So to convert back from a z-score to a raw score, what we do is do z, so 0.75 times our SD, 8, and then we add it to 76 to get 82. So that's how you would solve it when you're doing raw scores. How about percentiles? Well, you're probably going to have to break out that chart that we used a while back. Okay, so Misty scored at the 95th percentile. What is her percentile on the final exam? Let's keep going with the correlation between midterm and final at 0.5. So first, we can just write it up here. The percentile of her midterm, 95. So let's convert that to a z-score. If we use the table, we can go down the left side, or we can go look in the middle, find the percentile that matches up. Look to the left side, it's 1.6. Now look at the top of the table and go over, okay, and it looks like 0.05. Okay, so it'd be 1.65. Then what we can do is use the magic formula. So 0.5 times 1.65 equals 0.83. So now we have the z-score of her final. Let's convert that back to a percentile. So we just use that table. So let's go find 0.8 on the left side and go over to 0.03. Okay, so it looks like it's at the 80th percentile. So there we go. So if she scored a 95 on the midterm and the correlation between midterm and final is 0.5, we would predict that she would score at the 80th percentile on her final. Okay, so this is really important. The regression line always goes through the point of averages. Always. So if we look right here, we have this standardized equation where we have our standardized regression line, And you can see right there, it goes through our standardized coordinates of 0, 0, which is the point of averages for a standardized regression equation. If we talk about it in unstandardized coordinates, it would just be the mean of x and the mean of y. In this case, 2.8 and 69. Okay, so that was a review from class 14. Let's move on to some new materials. Okay, so moving on, let's talk about the z equals line and the regression line. So let's talk about a positive z equals line. So if you guys remember the equation for the z equals line and the positive one, it's z of y equals z of x. And remember, this is in standardized. So we can just plot it right here on a nice scatter plot, scatter plot. And you can see right here the positive z equals line. And you can see that it also goes through this right here, the point of averages. And it also goes through 1, 1, 0.5, 0.5, 0, 0, negative 0.5, negative 0.5, negative 1, negative 1. So we know if we plug in 0.5, z of y is going to be 0.5. So if we plug in 0, z of y is going to be 0. So this positive z equals line always goes through these 1, 1, 0.5, 0.5, 0, 0. Z of y equals z of x. That's the equation for the positive z equals line. Okay, so the positive z equal line, just like the regression line, always goes through the point of averages. And what's the slope? Well, we can figure it out. Let's find 2 points. Let's see, 0, 0, 1, 1. What's rise going to be? Okay, zy2 minus zy1. So we can use that right there. 1 minus 0 equals 1. Okay. Zx2 minus zx1. So 1 minus 0 equals 1. So look at that. 1 divided by 1 is going to be 1. That's the slope. So our standardized slope for the positive z equals line is 1. So let's look at the regression line. Always also goes to the point of averages. Let's look at the standardized slope right here. We know the standardized slope is beta, or the correlation coefficient. So both the regression line and the positive z equal line go through the point of averages. So you can see right here we have the positive z equals line plotted in a nice little red dotted line, and then we have the regression line in blue. You can see that they both intersect at the point of averages right here at 0, 0, or 420, 75. And notice that the slope of this, the positive z equals line, is almost always steeper than a regression line. There's only one case where they're actually the same. And this is with positive slopes, of course. So if we look right here, let's look at the correlation coefficient. We have a correlation coefficient between x and y at 0. You can see that we have these two lines as r approaches 1, as it increases, you can see that the regression line is actually approaching the slope of the z equals line. And only when r equals 1, a perfect relationship between x and y, is the slope of the SD and regression line the same. So you can see right here, going back down, and then going back up. So as r increases, the slope gets closer to the slope of the z equals line. Yeah, so the regression line gets closer and closer to the positive z equals line as r gets closer to 1. So the positive z equals line is almost always steeper than the regression line. So when r equals 1, the regression line and the positive z equals line are identical. So these are talking about positive slopes, so the positive z equal line almost always steeper than the positive slope regression line. Let's talk about negative slopes. So the negative z-equal line is almost always steeper than the negative slope regression line as well. You can just kind of put it in a mirror. So let's look at r equals 0. You have these two lines, the z equals line and the regression line, and let's approach -1. So let's go there. So you can see as r decreases and approaches -1, the regression line gets closer and closer to the slope of the negative z equals line. And only when r equals -1 are they the same slope. But that z equals line, negative z equals line, is almost always steeper than our regression line. Okay, so just like I said before, the negative z equals line is almost always steeper than the regression line. Only when r equals -1 is the regression line and the negative z equals line identical. So now that we know a little bit about our z equals line and our regression lines and how they kind of match up and how they go with r, let's try to do this. Let's calculate the unstandardized equation of the regression line. So we're going to need 5 different pieces of information. We're going to need the mean of y, the SD of y, the mean of x, the SD of x, and the correlation between x and y. So we have this scatter plot with a nice regression line on it. And here's our information. We see that the mean of y, 75, SD of y, 10, mean of x, 420, SD of x, 40, and the correlation between the two is 0.5. Okay, let's figure out the standardized regression equation. So we can use the magic formula. So we can just do this right here. So z hat of y equals r times z of x. We can plug in 0.5 right there, and then we can just use the same thing that we used before to figure out the actual equation. So we can find 2 points in line, calculate the slope, calculate the intercept. But look, since we're doing this, we can actually skip a few steps. We don't have to find 2 points, because guess what? We're going to learn a new equation for calculating this slope. And this equation is this right here. This is calculating the slope without using 2 points. If we have the correlation, we have the SD of y and we have the SD of x, we can find the unstandardized slope. So if you look at this right here, we just multiply r times the SD of y and then divide that by the SD of x. So let's do that here for this example. Plug in 10, plug in 40, and plug in 0.5. So 0.5 times 10, 5 divided by 40, we're going to get 0.125. Great. So now we know the slope. So now we can calculate the intercept. So this is just like before. We can put in our slope right there, and then we can just use any point from the line to actually get our general equation for that line. So let's just find a point. What point do we know? Oh yeah, we know the point of averages. The regression line always goes to the point of averages, so we just use 420, 75. Let's plug that in here, and here's our general equation for a line. So we can just plug in our x value, we can plug in our y value, and then we can plug in our slope. Do a little bit of math. So 0.125 times 420 equals 52.5. Subtract that off from 75, and we get the intercept being 22.5. We're not done yet because we need to just put it into our specific equation for the line to get this. So we know our slope, we know our intercept, so let's just plug it in. So our slope is going to be 0.125 times x plus our y-intercept of 22.5. So there we go. Now we just figured that equation out for that line. So steps again, just going back over this. Use the equation to find the slope. So this is an important equation. So unstandardized slope equals r times SD of y divided by the SD of x. Use the slope and the point of averages to find the intercept, and then just plug it back into the equation, just like we did before. So this is probably one of the most important things right here for this lecture. It's just that the unstandardized slope equals r times sd of x divided by sd of y, or sd of y divided by sd of x. And why does this make sense? Let's look at this right here. Let's look at our standardized regression equation. So we have our standardized regression equation right here, 0.5 times z of x equals z of y. And we can just plot some points on it. So 0, 0, 1, 0.5. And guess what? If we look at this, that would be the mean of x, the mean of y. If we look at that, this, look at the standardized point right here. Okay, 1.5. So 1, let's convert that to a raw score. Let's just plug it in right here. If we plug that in, you can see that we get SD of x plus the mean of x. So our raw score for this would be the mean of x plus SD of x. Okay, so that's a raw score of x equals the mean of x plus SD of x. Okay, what about the y value? So 0.5 times the SD of y plus the mean of y. So there we go. So if we actually did this right here, x, y equals the mean of x plus SD of x, comma, the mean of y plus 0.5 times the SD of y. Look at that. So we have our x and y values. So there we go, have our like formulas kind of representing that point. And what we can do is look at the rise. The rise is going to be our y. So let's just plug that in. Our run is going to be, oh yeah, so we get that part of the equation from there, and we get that part of the equation from there. So that's our rise. Okay, that's going to cancel out. So look, 0.5 times SD of y. Okay, let's just write that up there. Look at our run. So run is just x2 minus x1. So look, x2 would be the mean of x plus SD of x minus the mean of x. So look at that, right there, and look, those cancel out. So look, that's how we get our formula. That's how we get our formula for our standardized regression equation. So you can see right here that 0.5 is just our correlation coefficient. So if you just write r right there, so that's where that formula comes from. Okay, so again, if you want to find the unstandardized slope, we just use this nice formula right here, correlation coefficient times SD of y divided by SD of x. And you can think about it like this. If the ant goes sideways 1 standard deviation of x, he'll go up r standard deviations of y. So if you look at this, he goes right 1 standard deviation of x, he goes up r standard deviations of y. Think about if the correlation coefficient is 0.8, he goes right 1 standard deviation of x, he goes up 0.8 standard deviations of y. Think about correlation coefficient 0.3. So the ant goes right 1 standard deviation x, he goes up 0.3 standard deviations of y. Nice way to think about it when we're talking about standardized. So again, this unstandardized formula, r times SD of y divided by SD of x. If ant goes sideways 1 standard deviation of x, he'll go up r standard deviations of y. Okay, so now let's move on to RMS error of prediction for regression. So as we learned before, RMS, root mean squared, we learned that back when we were doing, figuring out z-scores and correlation coefficients and everything. So let's talk about prediction error. Prediction error is just how much our prediction is off. So we have a regression line, and not all those points always lie on that regression line. we have a difference between the predicted value and the actual value. So you can see right here, we have the regression and line between IQ and GPA. We got a nice scatter plot. You can see that this is 700 people. The SD of Y equals 0.304 and the R is 0.446. So that person, he's not on that regression line. Let's draw a line down and see where it intersects with the actual regression line. And you see that gap right there, how far he's off? That error, that's called error. That's 0.6. Because if we were to use the regression equation to figure out his value, we would say he lies right here. But in fact, he actually is up here. So we have an error, 0.6. And every one of these dots have error. So we can think about this guy, he's down here. Draw a line up to the regression line, and we can calculate that. That's about negative 0.75. So we can figure out the mathematical formula. It's pretty simple. We have y hat 1, it's the predicted value for the first individual, and we have y hat, the actual value of that individual. So we also call that y observed. And if we want to figure out the error for that person, we just say the error for individual 1 equals the y observed minus predicted y for that individual. So nice little formula for figuring out the error for that one individual. And we also call this a residual. So guess what? We have individual 1 right here. He's at 73. We would predict right here where it would actually be on the regression line. We would predict that it would be at 2.61, but look, he actually scores at 3.42. So what we can do is take these scores and do a little bit of math and get 0.81. So we have a 0.81 error. We can do that for every one of the 700 individuals, which is on the scatter plot. Do the individual 2. Let's see, 127, 309, but his actual score is 2.41. So we got an error right there, negative 0.68. So we can do that for all 700 individuals. What if we want to know the typical size of the errors? How much our regression is off in general, the typical size of these errors. We can just say, let's just average the errors. Let's look at that. Guess what? It sounds good, but it doesn't work. Why doesn't it work? Guess what? The sum of the errors is 0, and the average of the errors is also 0. So we've seen this before, right? Where do we see this? Wasn't it if we did what? Deviations, yeah. So what worked with deviations? What do we do to deviations? Oh, we squared them. And then we took the root mean squared. So that's where this root mean squared error is going to come from. Okay, so standard deviation. This is just root mean squared deviation. What do? We squared all of our deviations. We summed the squared deviations. And then we found their mean. And then we took the square root of that mean. That's how we figured out root mean squared, or SD. So let's think about it in the sense of errors. So RMS error of prediction. We square all of our errors. We sum the squared errors, called SSE, and then we can find their mean. So mean squared error. And then as we take the square root of it, we get our root mean squared error. And this just gives us the typical distance of the SD gives us the typical distance of individual from the mean. So we can think of RMS error of prediction as the typical difference between observed values of y and the predicted values of y. So let's look at the two ways to calculate RMS error. The long way, guess what? We can calculate all 700 errors, probably using Excel or something like that. Then we can calculate the mean squared, the root mean squared of all those errors by, squaring them, taking their mean, and then taking the square root of that. So yeah, square all the errors, sum the squared errors, find their mean, and then calculate the square root. So definitely know what's going on here. just like standard deviation, but we're using errors. So in our example, we get RMS error using the long way, using Excel 0.272. That's the SD of the errors. So RMS error is just the SD of these errors. So what's the mean of the errors? What's the mean of the errors? Okay, so let's look at the short way to calculate RMS error. We can just use a nice formula. So this is another formula that's really important for this lecture. So look at this formula right here. It's the square root of 1 minus the correlation coefficient squared. Then multiply that by the SD of y. So in our example here, we can just plug in everything we have. So we have the SD of y, 0.304. We have the r, 0.446. So let's plug that in. First, you want to square 0.446 to get 0.199. Take 1, subtract it off. 0.801, take the square root of that. And then multiply that, which is 0.895 times 3.04 to get 0.272. Same way as the long way, same answer. So we always recommend use the short way. There's no reason you should do the long way. You can do the short way, much easier. But you should understand what is happening in the background. So you should understand the long way and why it works. What's RMS error when r equals 1? Let's think about it. Where are all those dots on that line? Where are those dots if the regression uses a correlation coefficient of 1? Guess what? If we do 1 squared minus 1, 0, 0. There's no error because all those dots lie on that line. So you can just think about it like that. There's no error because it's a perfect relationship between x and y. So that's just a very brief overview for some of you guys that missed class 15 before spring break and before the whole lockdown happened. So hopefully that will help you guys out. I will upload this to YouTube, and hopefully this will give you a nice little overview just to help you for exam number 2. You guys have a good rest of your day and enjoy your homes.